Period is the time taken for one complete oscillation. That's a period. And then what does frequency mean? That's a good question.
How many times, how many oscillations happen in a certain amount of time?
Per unit time.
Per unit time.
So it's the number of complete oscillations per second or per unit time, right? Per unit time. Very good. And you'll remember F was equal to 1 over T, right?
Yes.
Remember that?
Yeah.
F is equal to 1 over T. Then there's a quantity we talk about now in A level, and that is angular frequency. Angular frequency, or omega, right? And this is defined as the rate of change of angular displacement. The rate of change of angular displacement. So of course the angular displacement is measured in radians, right, for a complete circle.
Yes.
We use radians more, not so much degrees. So I could calculate omega as 2 pi over t, right? 2 pi is a complete circle, right?
Yes.
Where before maybe you might have used 360, and t is the time for complete rotation.
Yes.
So this displacement is measured in radians. So the units would then be radians, rad s minus 1, okay? That's the unit. Okay, sound about right?
Yes.
Right, so this is just F is equal to 1 over T, and omega is 2 pi over T. Got it?
Yes.
Right, lovely. Moving on. Now let's define what simple harmonic motion is. Let's define what simple harmonic motion is. Right. Simple harmonic motion. What do you think of when you think of simple harmonic motion? What does that mean to you?
Simple harmonic motion, like perfect oscillations.
Yeah, that's good. I like that. Perfect oscillation. That's a good one. So say, for example, I have a spring, right? I have a spring, and the spring looks something like that. And right now, the spring, I have not extended the spring. Of course, maybe if there's a weight here, there might be some extension, but we're saying that the spring is kind of at rest, isn't it?
Yes, yeah.
The spring is kind of at
Rest
in that position. If I were to pull the spring downwards, let's say I pull the spring up to 5 centimeters downwards, right? And then the new position of the spring is down there. What will the spring do? What is the spring feeling? If the spring wants to do what? What does
the spring wants to pull it back up.
Correct. So suddenly what you're getting is a force wanting to pull it back up. Is that making sense, right?
Yeah.
And then of course the force will pull it back up because the spring has been stretched, hasn't it?
Yes, it has.
It's been stretched, so it wants to pull the thing back up. It goes there, but of course it's going to overshoot, isn't it? And it'll probably overshoot up to this position somewhere there, right?
Yes. Yeah.
Where maybe it will overshoot by another 5
centimeters.
Does it make sense, right?
Yes, yeah.
And then of course what you've done now is instead of extending the spring, you've compressed the spring. Now the spring wants to do what?
It wants to go back down now.
Wants to push it back down.
Push it back down, yeah.
Does it make sense, right?
Yes, yeah.
So you have this force that's generated by either compressing the spring or extending the spring, right?
Yeah.
And of course a force produces an acceleration.
Yeah.
Does it make sense, right? So this is the definition of simple harmonic motion. Simple harmonic motion is defined as the oscillation in which the acceleration, or the restoring force, right? Or restoring force, because this is the force we're talking about, not to put it, or the restoring force, the acceleration or restoring force is directly proportional to the displacement, right? So basically, if I was to pull this spring even further, instead of just 5 centimeters, maybe I pulled it up to 7 centimeters, would that force be stronger or weaker?
It'll be stronger.
It'll be stronger, right?
Yeah.
Do you see what I mean? So the more extension you give it, or the more displacement you give it, the more force, or the more acceleration.
Yes, okay.
So the acceleration is what? Directly proportional to the displacement.
So sorry, you said the oscillation, the full definition is
It is oscillation in which? Yeah, the acceleration or restoring force is directly proportional to the
acceleration or restoring force,
restoring force. But you don't need to give both for the definition, just acceleration is enough.
Okay.
Just say acceleration is directly proportional to the displacement. But they are in opposite directions. They're in opposite
directions.
Does it make sense, right? They are in opposite directions. You displace going downwards, but the force wants to pull it upwards. Does it make sense, right? They are in opposite directions. So acceleration directly proportional to x, isn't it? More a, more x, more a. That's an example, right?
Yeah.
If I introduce a constant, a is equal to omega squared x. This is the sort of constant between them. But because they're in opposite directions, there's a minus. There's a what?
Minus.
A minus. Do you get this formula?
Yeah. Acceleration proportional to extension.
To displacement.
Displacement, sorry.
Yes.
And then acceleration is equals to minus omega squared times displacement.
Correct. Okay. And of course, this negative sign shows, what does it show? That they are in
opposite
directions. Very good. In opposite directions. That's what the negative sign indicates, that they are in opposite directions. Again, omega is angular frequency. What is omega?
Angular frequency.
That is the angular frequency squared. X is displacement, right?
Yes.
Okay, that's clear enough, isn't it?
Yes.
So, what shows that they're in opposite directions?
The negative sign.
Very good. Very good. So a very important graph that they often give you in the exam is A on this axis and X on that axis, right? And the graph will look something like this. It's a straight line. So it should be straight. But mine is not straight. It should be a straight line. Like that. It should be a perfectly straight line. Through the origin, right?
Yes.
All right, through the origins. And then you need to be able to tell, like, if I linearize this equation, A is equal to negative omega squared x. A is y. See what I mean by linearize? That's y. Yeah. And on the axis, x obviously.
Yeah.
But x being for displacement. And that means, what does your omega squared represent?
Your gradient.
Good. That's your gradient. Very nice. Does this make sense, right?
Yes.
So in the exam, you should write gradient, right? Gradient is equal to negative omega squared. Or rather, gradient is equal to
negative omega squared.
Or omega squared is equal to negative gradient. Does that make sense, right?
Yes.
But of course, in your working, your physical working, you don't need the negative sign.
Yeah.
You just do rise over
run,
and that will give you omega squared. But really important to remember that rise over run, you should equate to omega squared. Okay?
Yes.
Rise over run gives you omega squared.
Perfect.
Perfectly understandable, right?
Yes.
All right, good. Now, let's move on. Let's talk about the displacement of an object. Displacement against time graph. Displacement time graphs. Okay. If you're to draw the graphs, right, where this is displacement, obviously the displacement becomes positive, it starts vectors are positive, reaches a maximum value, goes back to the original position, then becomes negative going in the opposite direction, and so forth, right?
Yes.
Does that make sense, right?
Yes.
So come back to a spring, right? So if I'm starting the spring from the rest position here, you see that? Mm-hmm. If it extends going this way, it's becoming maybe positive, right?
Yes.
It is positive, right?
Yes.
Maybe this is 3 centimeters as an example. Then it goes back again, 3, 2, 1, and then
it goes
0.
into the negative.
Then 0, and then maybe -1, -2, then -3. And is that making sense, right?
Yeah.
So if you're to draw the graph of that, it would look something like this. It would look like this. Is that making sense to you? Okay. So this is assuming you're starting it at the rest position. You're assuming you are starting at rest position. You get that?
Yeah.
You assume you're starting at rest position. So here it's now back at rest position, for example, right? This is now back at
Rest position.
Rest position. Then now it's going into the negative. It's overshot the rest position. You know what I'm saying, right?
Yes.
And then back at rest, coming back into the positive again, and so forth, right?
So what's on the so displacement is on the y-axis.
Correct. And time
on the negative
on the
x-axis.
Very good. Time on the x-axis. Does this graph look familiar to you in any way?
Yes, it does.
What does it look like?
The sine graph.
Very good. So the formula is actually x is equals to x naught for maximum displacement. Max displacement is sine, open brackets, omega t. Okay. And of course everything's in radians, right?
Yes.
Everything in radians. So this is your displacement at any point, because this displacement is changing, is equal to x naught sine omega t. So which of these quantities never change? X naught is a constant that will never change, right? It's a constant value, and so is omega. There's a constant. Your constantly changing variables are your x, because your displacement will become positive, less
And
positive,
then
negative,
yes.
and your time, of course, is also changing because time stops for no man. You get it, right?
Yes.
So those are your items to be aware of. However, if I start the graph not at rest position, because sometimes you might want to start the graph at maximum displacement. Is that making sense?
Yes, then it's a cos
graph, brava. Well done. It's a cos graph. As an example, right? Could start off something like that, isn't it? Where this is now x naught, isn't it? And negative x naught. X naught and negative x naught, right? Making sense?
Yes.
And then this time it's x is equal to what? Give me the equation.
X is equals to x naught.
Well done.
Cos
Omega
times time.
Omega t. Well done. Do you understand that?
Yes.
Right. Nice and easy, right? Mm-hmm. Very good. Now, if I was to ask you, when do you expect the graph to be, or the spring to be moving fastest? Sorry, I've overshot. Right? Do you think let's look at the spring again, right? Is it fastest here at the start?
I'd say it's
and
fast.
in the middle? Is it fastest here in the middle?
Yeah, I'd say it's fastest in the middle.
Correct. Not at B or
A
C.
or C. Sorry.
Because,
sorry.
correct.
Yeah.
Correct. Because at this point, we assume the speed is 0, isn't
Zero
it?
because
at
it's
maximum.
and then it's starting to come
Then
back
it
down.
starts to increase, and then it becomes fastest here at the rest position.
Then it starts to decrease.
And then it starts to decrease
Yeah,
until
makes
it
sense.
finally stops, isn't it? Right?
Yeah.
So the fastest speed is here. Mm-hmm. And in the rest position. Okay? That's the fastest speed, isn't it? When it's in the middle of the motion, isn't it?
Yes.
Right. So speed is fastest at rest position. At
Rest position.
rest position, right? And the formula for speed is V max or V fastest is equal to omega x naught is equal to omega x naught. Even though we use the maximum displacement, weight is not fastest, but the formula has, we use that. Does that make sense, right?
Yes.
However, V is a variable. V is changing, isn't it?
Mm-hmm.
V, which is constantly changing, is equal to plus or minus. Why plus or minus? Because it can be going in either direction. It's going
Either up or down.
Yes,
Yeah.
and then you see what I mean, right? So if up is positive, down is negative, for example, right? Is equal to x naught squared minus x squared. Mm-hmm. Got that?
Yes.
V is equal to plus or minus omega square root x naught squared minus x squared. What does x naught represent?
X represents x naught represents maximum displacement.
Very good. It's max displacement. And then, of course, x will then be the displacement at that particular position, isn't it?
Yes, yeah.
Max displacement. And then x is the changing displacement, isn't it?
Mm-hmm.
Changing displacement. Right. And omega, of course, is still angular frequency. Angular what? Frequency. Make sense?
Mm-hmm.
Good. Very good. So far, so good. So far, so good. So while we are discussing velocity, I want to discuss two graphs with you, right? While we're discussing velocity, I want us to discuss two graphs.
Angular frequency.
So if you're to plot a graph, right, for the velocity, are you with me?
Mm-hmm.
Velocity against displacement. Please note, this is not velocity against time.
Velocity.
Velocity against
Displacement.
displacements, maybe in centimeters or meters, meters. So
Yes.
velocity will be in meters per second, and this is x in meters, right? The graph should be elliptical. The graph should be
Elliptical.
like this, right? So obviously when your displacement is 0, you have maximum velocity, don't you?
Yes.
And then of course, as soon as you pass that maximum point in the middle, it starts to what?
Velocity
Decrease.
starts to decrease.
Yes, but of course it's the decrease makes sense that it's that it's not a constant decrease, right? So it's not a straight line, is
Yeah.
it, right? If the deceleration was constant, it would be a straight line.
Straight line. No, yeah.
Does it make sense, right?
It makes sense.
But of
yes.
course, in this case, what's happening to the force? The force is getting greater and
Greater.
greater, which then means that the rate of deceleration should be
Greater and greater.
and greater. Does it make sense, right?
So then when it cuts the x-axis.
So at this point, it's now at maximum displacement, right? It's at the top.
Okay.
It's at the absolute top. Right, of the
Yeah.
spring. That's x naught. And then what happens to it? It starts to increase in velocity.
again.
But because this time it's now in the opposite direction. So it's negative, isn't it?
Yes.
Is that making sense? It's
Negative.
negative. Is that making sense? Like that. And then at this point, you've got maximum speed. This is at the absolute bottom of the motion. From the absolute bottom, it starts to what? So this is maximum displacement, right? At the absolute top, for example. And then from then on, it starts to...
The displacement is decreasing.
So now it's at what point is this? What point is this? This is now in the...
It's at
center.
the other...
It's in the center again. We're
Yes,
back in
yes,
zero.
yes,
So it's
yes.
the absolute center. Again, the rest position. Right? Rest position. And then what does it start to do again? It starts to, from rest position, it starts to decrease. Decrease. Until it gets to the other maximum, negative x naught. And then again, at this point, it's at the absolute bottom now, right? So this is the absolute top, as an example. And this is now the absolute bottom of the motion, yeah?
If it... okay, no, I get it.
You get that, right?
Yeah.
Absolute bottom. And then here is the rest positions. I mean, this is the rest position. Central rest position. And this is also the other central, when the speed is maximum, isn't it?
Yes.
Central rest position when the speed is maximum. Okay, so the graph is elliptical. The graph is
Elliptical.
elliptical. You need to use that word when describing it. It is elliptical. If they ask you to use words. Okay, so this is speed against what?
Speed against displacement.
Good. So let's recap. So we learned about acceleration against displacement, right? Which was a straight line.
Yes.
Straight line, right? Where the gradient represents what?
The gradient represents the W
Squared.
The W squared.
Omega
yes.
squared.
Omega
Angular frequency squared. And now we've just discussed velocity against displacement. What kind of a graph is it?
It's an elliptical graph.
Correct. However, when I draw displacement against time, I get this kind of a graph, isn't
A
it?
cos graph or sine graph.
Depending on where you're starting it,
Yes.
isn't it?
Yeah.
Right? Good. And if you're starting it in the rest position,
It's a sine graph.
If you start it at maximum displacement,
It's a cos graph.
It's a cos graph. But so therefore, you'd expect if you draw V against T graph. Now this is V against what?
Time.
T. Not V against X, but V against
T.
Because V against X is what we have above, isn't it?
Yes.
V against T looks very similar to the other graph, depending on how you've started it. That makes sense, right?
Yeah.
Because as you will learn, because as you know now for your A-level maths, the derivative of cos is sine,
And
it's negative. It's negative sine, and derivative of sine is positive cos.
cos.
So basically, a cos graph becomes a sine graph, a sine graph becomes a
cos graph.
That makes sense, right? So
Yes.
it will have the same sort of shape, just depending on where you are
starting
it.
from.
Correct. So if, for example, I'm going to change this back into x. If the x graph was a sine graph, you see my meaning, right? If the x graph is a sine graph, the v graph will become a what graph?
A cos graph.
Correct. Which
Okay.
you see, right? Because the differentiation or the gradient, is that making sense,
Yes.
right? Is a cos graph. So it should then become a cos graph. Is that making sense?
Yes.
I'm trying to find, so it's like that. Like that. So these are like defining points, isn't it, in the motion? You get it, right? That this turning point is the 0 point. You see, if the turning point on your x is a maximum point, it's a 0 point on the v. Is that making sense?
Yes.
maximum V there. And again, that turning point here should make a 0 point on the V. Is that making sense? Should make a 0 point on the V. And so forth. Okay? Etc. So please note, maximum point on X is a 0 point on V.
V,
Is that making sense?
Yeah.
And of course, a 0 point in the X is now a maximum point on the V. Because of the nature of the graph, etc. Okay, well, that makes perfect sense, right?
Yes.
And then acceleration is also a reflection of that.
Yes.
Good. I hope that makes perfect sense.
It does. It makes sense.
Maybe. So while we're still there, when do you get maximum kinetic energy? When the speed is?
The speed is at its max.
Correct. So back to a spring again, right? A spring. This was the rest position, and we extend the spring by a few centimeters. Remember, we stretch it by, say, 5 centimeters, right? And then, which means when it reflects up backwards by another 5 centimeters upwards, isn't it? So I'll ask you again, at point A, B, or C in the motion, at what point do you have, as it does, remember, so we take it from here, it goes up and comes back. I mean, it moves up and down, right? At what point do you have maximum speed?
B.
Correct. Max speed is B in the middle or the rest position. So this is max speed, and therefore max what?
Max kinetic energy.
Well done. Max kinetic energy. Are you with me? So now, and then where do you think you get maximum elastic potential energy?
At A and C.
Good. At the maximum there is max potential. And here is also max potential. All right? Does it make sense to you?
It does.
Wonderful. Max potential. But of course, at any point, the kinetic energy plus the potential energy will equal to some total, isn't it?
Yes.
All right? Or some total. Only on the extreme, only at point A is all the energy potential, and only at point B is all the energy kinetic. And at point C again, all the energy is
elastic
potential.
Yes.
You understand that, right?
Yeah.
But somewhere in the middle, you get a mix of both.
Yes.
Somewhere in the middle, you get a mix of
both,
right? The formula for the kinetic energy is equal to half m omega squared brackets x naught squared minus x squared, right, for kinetic energy at any point in the motion. And the formula for potential energy at any point in the motion is half m omega squared x squared. You understand that?
Yes.
And then the formula for total energy, say for example when potential is at the maximum point, is half m omega squared x naught squared. That's total energy when you're a combination of both, right? Kinetic and potential. Okay. Perfect sense?
Yes.
All right. Marvelous. Marvelous. Marvelous.
Okay, let me write this formulas quickly. So kinetic. The kinetic plus the potential is equals to the total energy.
That is correct. Because remember, you have a mix of both during the motion, except for those special points, isn't it?
Yes.
The special middle, the special top
and
end,
the top.
And top or bottom, isn't it? Right? Those are special points where you have either only kinetic or only potential, isn't it? Right?
So do I have to memorize these formulas now?
To some extent, you probably should learn them, yes. There are only three.
Still.
There are only three.
And for the potential energy, half m x squared.
But try and make sense of the formulae, right? Rather than memorize them necessarily. Try and make sense of where they
come from.
Yeah.
Yeah.
Try and make sense of them.
Okay.
If I was to draw a graph, this is the last thing now, and then we're going to take a break. If I was to draw a graph of energy against displacement again, against what?
Displacement.
Which is your x, isn't it?
Yes.
Against x. The total energy will remain the same.
Yes.
Does it make sense? Even if you're starting from here,
Energy
negative
against...
x naught. Of course, does it make sense to you that the total energy will remain the same?
Yes, because if you're at like point A, all the energy will be at max elastic potential. If you're at point B, all the energy will be at max kinetic, and if you're at any other point, both kinds of energy will add up to make that total.
Correct.
Yeah,
so if I
makes
come
sense.
back to the spring, let's assume, for example, at point A, our total energy was 30 joules, as an example, right? Somewhere in the middle here, you might, not in the middle, but somewhere in the motion, you might have 20 joules of potential, which means that you'll have 10 joules of kinetic. And then, of course, as you get closer to the middle point, you're getting more kinetic, isn't it, right? So maybe you might have 25 joules of kinetic and 5 joules of potential. Until you're bang in the middle, at that point, it's all
kinetic.
Kinetic, that makes sense, right?
Yes.
But the total is still always 30, right? I think you've understood that, right? So now, when did we say kinetic energy was the highest?
At point B, the middle, the rest position.
The middle point. So where displacement is zero, right? That's the middle position. So obviously our maximum is there. And so if the graph looks something like this, do you know what I mean? It's a curvy thing. And the other one is like that. Does that make sense?
Yeah. Wait, sorry. What's this?
This is the kinetic energy graph.
Okay.
Which of course will be maximum bang in the middle, isn't it?
Yes. Yeah.
And of course potential will be maximum where?
Potential would be maximum. It'll be a concave. It'll be like, so it's maximum
at the start, isn't it? Let's try that. So it will be maximum here at the end positions, isn't it? These are the maximum potential points at the very maximum displacements, which of course then to be zero where? In the middle, isn't it? Expected to be zero in the middle, right in the middle of the displacement where there's no displacement, and then it curves up in that way. Right. I hope that makes perfect sense.
It does make sense. It does.
Okay. Good. So this is the PE graph, potential, elastic potential energy graph. Okay, that graph is always like that. Right, and then we'll take a break, and then we'll pick up on damped motion.
Perfect.
In a sec.